general solution as y of t is equal to, and let's go ahead and write our a solution to our homogeneous equation first, and then we will add that particular. So our homogeneous solution was C1 cosine of 2t plus C2 sine of 2t plus, and here is our particular solution, cosine of 2t multiplied by the natural log, I guess go ahead and put parentheses there, of cosecant of 2t plus cotangent of 2t minus 1. And that is our general solution. See if I can make that box a little bit nicer. Okay, let's look at our next problem. Find a general solution to the differential equation. And here you can see we have a secant cubed of theta on the right-hand side. Second derivative plus y of theta equals that a secant cubed. Okay, so our set of functions for our homogeneous equations would be y1 of theta is equal to the cosine of theta, and y2 of theta is equal to the sine of theta. And applying the method of variation of parameters, we seek our particular solution of the form yp of t equals v1y1 plus v2y2. So let's go ahead and write our system of equations. We have v1 prime of theta multiplied by the cosine of theta plus v2 prime of theta multiplied by the sine of theta is equal to 0. And now our second equation in our system, those derivatives, the opposite of v1 prime of theta sine of theta plus v2 prime of theta cosine of theta. And that's going to be equal to the secant cubed of theta. That is our f over a. Now we're going to go ahead and multiply this first equation by the sine of theta, and our second equation we will multiply by the cosine of theta. And we will then add them together. So let's see what we have here. We have v1 prime of theta sine theta cosine theta plus v2 prime theta sine squared is equal to 0. And then we have the opposite, of v1 prime of theta sine theta cosine theta. That's our terms that are going to cancel when we add them together, plus v2 prime of theta cosine squared theta is equal to, and now we'll have the secant squared of theta. So adding these together, as you can see, we will have v2 prime of theta multiplied by the sine squared theta plus cosine squared theta is equal to the secant squared theta. And you can see that v2 prime of theta is equal to the secant squared theta. So remember, we can go ahead and find v2 of theta by integrating. So we have v2 of theta is going to be equal to the integral of the secant squared theta d theta, and that's equal to the tangent of theta. So now we want to go back and use equation 1, and we will find v1 prime of theta. So we have v1 prime of theta multiplied by the cosine of theta plus, and let's go ahead and put V2 prime of theta there, which is the secant squared theta multiplied by the sine of theta is equal to 0. And we have that V1 prime of theta is the opposite of the secant squared theta. And if we took the sine and divided by the cosine, we would have then the tangent of theta. So looking for V1 of theta, we will integrate V1 prime. So the opposite of the secant squared theta, tan theta d theta, and the integral of the tangent multiplied by the secant squared is going to give us that tangent squared. So that's negative 1/2 tangent squared of theta. So now we can write our particular solution as negative 1/2 tangent squared theta cosine of t. I think I used the t up here. I don't know why I did that. Should be theta. Plus the tangent of theta sine of theta. And we can then see that that's equal to 1/2 the tangent of theta sine of theta. And I can actually show you that. That would be equal to negative 1/2 sine squared theta over cosine squared theta multiplied by the cosine of theta. And then actually I can go ahead and show you this. And so you can see that this is equal to negative 1/2 multiplied by the sine squared theta over the cosine of theta plus the sine squared theta divided by the cosine of theta. And that just leaves us with 1/2 of the tangent of theta multiplied by the sine of theta. Go ahead and have one half of these left. And that, of course, is equal to 1/2 multiplied by the tangent of theta multiplied by the sine of theta. So with that, we now can give our general solution y of theta, and that's equal to our particular solution plus the solution to the homogeneous equation, and that's equal to 1/2 tangent of theta sine of theta plus C1 cosine theta plus C2 sine of theta. Okay, let's take a look at our next example. Find a general solution to the differential equation, and you can see our f of t is 18t squared. We take a look at our homogeneous equation, which is y double prime plus 5y prime plus 6y is equal to 0. Our auxiliary equation is r squared plus 5r plus 6 is equal to 0. And we have r plus 2 multiplied by r plus 3. And so we have r1 is equal to negative 2 and r2 is equal to negative 3. So a solution, a general solution to the homogeneous equation is y h of t is equal to C1 e to the negative 2t plus C2 e to the negative 3t. So now we are going to use the method of undetermined coefficients to find a particular solution to the non-homogeneous equation. So now we are going to use the method to find our particular solution. So we have yp of t, and let's just go ahead and use yp is equal to a2t squared plus a1t plus a naught. And keep in mind that is because we have this t squared. So we want to make sure we use all terms. So now we have yp prime is equal to 2a2t plus a1, and y double prime is equal to 2a2. So we can see here that when we substitute these into the original equation, we have, that 6a2 t squared plus 10a2 plus 6a1t plus 2a2, let me move this down here, plus 2a2 plus 5a1 plus 6a naught is going to be equal to 18t squared. I'm just going to move this over just a touch so I can get my t squared there. Okay, so taking a look at this, I can leave that to you. We have a2 is equal to 3, a sub 1 is equal to negative 5, and a naught is equal to 19/6. And you'll have to do that on your own, or you can verify. Okay, and so now we have that particular solution is equal to 3t squared minus 5t plus 19/6. So now we can come up with our general solution, which is that particular solution plus the homogeneous solution to the homogeneous equation. And we come up with, I'm just going to go ahead and do y of t. And we have 3t squared minus 5t plus 19/6 plus c1e to the negative 2t plus c2e to the negative 3t. Okay, let's take a look at our next problem. Find a general solution to this differential equation. As you can see, we have t to the negative 3 multiplied by e to the 3t. So this is our f of t. we can see that our auxiliary equation, we will have a double root. Let's take a look at that. So we have r squared minus 6r plus 9 is equal to 0. So we have r minus 3 squared. So we have r is equal to 3, and we do have a double root. So now we have that y1 of t is equal to e to the 3t, and of course we add that or multiply that by an extra t, so te to the 3t. So now with that, we will have our particular solution, and let's look at the form of that. We will have yp of t is equal to v1 of t multiplied by y1 of t plus v2 of t multiplied by y2 of t. We're going to go ahead and satisfy our system, write our two equations of our system, and we have e to the 3t v1 prime plus te to the 3 v2 prime is equal to 0. Let's write our second equation of our system. We have 3e to the 3t multiplied by v1 prime plus 1 plus 3t e to the 3t v2 prime, and that's equal to t to the negative 3 e to the 3t. That is our f of t. Okay, we are going to subtract the first equation from the second one after we multiply that first equation by a 3. So let's go ahead and multiply this first equation by a 3, and we have 3e to the 3t v1 plus 3te to the 32 v2 prime is equal to 0. And then we will have our second equation, and we're going to be subtracting that first equation from the second equation. So we will take the opposite of this, and then we will come up with, and you will see when we do that, this 3t and this 3t will cancel each other out when we do subtract. So we end up with e to the 3t v2 prime is equal to that f of t. So we have t to the negative 3 e to the 3t. Okay, so v2 prime is going to be equal to t to the negative 3. We now have then that v2 of t is that integral, the integral of t to the negative 3 dt, and of course we have negative 1 over 2t squared. Okay, we're going to go back to that first equation right here, and going back to that first equation and substituting v2 prime in, we have v1 prime is equal to the opposite of t, v2 prime, and that is going to be equal to negative t to the negative 2. So that's v1 prime. Therefore, v1 is going to be the integral of that, and that's going to be equal to 1 divided by t. So now we can come up with our particular solution, and that's equal to 1 over t e to the 3t minus 1 over 2t squared t e to the 3t, and that simplifies to e to the 3t divided by 2t. So now we have our general solution, and that is, of course, going to be our particular plus our homogeneous. We're going to have to write it right over there. And that's going to be e to the 3t divided by 2t plus c1e to the 3t plus c2t e to the 3t. Okay, let's see. Let's take a look at our next example. Use variation of parameters to find a general solution to the differential equation given that y1 and y2, of course we can see they are linearly independent and they are given to be solutions to the corresponding homogeneous equation for t greater than 0. Let's first write this differential equation in standard form. We will divide every term by t squared, and we will come up with y double prime minus 4 divided by t y prime plus 6 divided by t squared y is equal to t plus t to the negative 2. Now keep in mind that this here is now equal to g of t. Let me just put that right below. So yeah, I can put g of t equal to. Okay, so now we are given two linearly independent solutions here and here. These are linearly independent. And what we're going to be doing here is coming up with those integrals that we were given. So I wanted to try using the Wronskian. So let's go ahead and do that. The Wronskian of y1, y2 of t. And that's going to be equal to t squared multiplied by 3t squared minus 2t t cubed, and that's going to be equal to t to the 4th. So t to the 4th is what is going to be in the denominator of our integrals, okay? And let's go ahead and remind ourselves about that Wronskian. And that's going to be y1 of t multiplied by y2 prime of t minus y1 of t prime, multiplied by y2 of t. And that's what we've done here. And we've gotten that equal to t found that to be equal to t to the 4th. Now, let's go ahead and take a look at those integrals that we talked about. So keep in mind that these integrals that we used, the 1 of t, and so these were equal to the opposite of f of t, y2 of t, divided by a multiplied by that Wronskian. I'll just put that a right in front of that, dt. And likewise, v2 of t is equal to the integral of f of t, y1 of t, divided by a multiplied by the Wronskian of our two functions with respect to t, dt. And again, this here, this t to the fourth, is going to be equal to this Wronskian. So let's go ahead and plug what we have in. So we have the opposite. And remember, we're going to put our g of t here. So really, in this case, this is going to be g of t. But we just have that formula, so it's not a big deal. And so we have the opposite of g of t, which is the opposite of t plus t to the negative 2. And then we still have y2 of t, which is t cubed, divided by a is equal to 1, and t, the Wronskian, is t to the fourth dt. And you know what? Let's just go ahead and do that side by side here. We're just going to have g of t, which is t plus t to the negative 2. And we're going to multiply by y1, which is t squared, and divide by that Wronskian, which is t to the fourth. Okay? And so now we can come up with, and we can simplify those a little bit. This simplifies to the opposite of the integral of 1 plus t to the negative 3 dt. And of course, that's equal to 1/2 t to the negative 2 minus t, ignoring our constant of integration. Here for v2 of t, we will have the integral of t to the negative 1 plus t to the negative fourth dt, and we will have the natural log of t minus 1/3 t to the negative 3. And you can see here we'll have a t cubed divided by t to the fourth, and so forth. The algebra is pretty simple. Okay, so what have we come up with now? So with these V1 and V2, we can go straight to our particular solution. And remember, that's V1y1 plus V2y2. And now that we have V1 and V2, we have 1/2 t to the negative 2 minus t, and then of course we have to multiply by y1, which is t squared, plus the natural log of t minus 1/3 t to the negative third multiplied by t cubed. And that does simplify nicely to t cubed multiplied by the natural log of t minus t cubed plus 1/6. And you can go ahead and see how that works there with that negative 1/3 and then that 1/2. Okay, so now we can come up with our general solution, and we have y of t is equal to t cubed natural log of t minus t cubed plus 1/6 c1 t squared plus c2 t cubed. And if you'd like, we could actually put these terms together here. So we could say that we could have c3 equal to c2 minus 1, and that would give us, let's move that over here. And it doesn't have to be done that way. And to arrive at our general solution, t cubed natural log of t plus 1/6 plus c1 t squared plus c cubed t cubed. And I can just see right here, I just did not put that plus sign in there, but now that makes sense. Okay, Let's give another one of these a try. Here we're given the same thing. We're given two linearly independent solutions to the corresponding homogeneous equation. And we do have t y double prime minus t plus 1 y prime plus y equals t squared. Let's go ahead and write this function in standard form, dividing every term by t. So we have y double prime minus t plus 1 divided by t y prime plus 1 over t y is equal to t. So we now see that f of t, or we could call it g of t here, we could call it g of t, is equal to, let's go ahead and call it g of t, since this original was what we called f of t. Okay, so now we were given two linearly independent solutions here, y1 and y2. And so we can now write that the Wronskian, let's compute the Wronskian of those two solutions with respect to t. And we have e to the t multiplied by t plus 1 prime minus e to the t prime multiplied by t plus 1. And you can see that we have the Wronskian equal to the opposite of t, e to the t. Okay. And let me go ahead and work that out. So we would have e to the t minus e to the t multiplied by t plus 1. And that's where we come up with, whoops. Okay, so we will use that Wronskian in our integrals that will help us come up with the 1 of t. Of course, we have that integral, and that numerator is the opposite of g multiplied by y2 of t divided by that Wronskian, which will be negative t. You know what? I'll just go ahead and write a, which is 1 multiplied by the Wronskian, and that v2 of t will be the same. Put these side by side, and just with, of course, no negative, and we will have y1 of t and then we have divided by that a, which is going to be 1 dt. Okay, so let's go ahead and fill these in. We have the opposite of t multiplied by t plus 1, all divided by the opposite of t, e to the t, dt. And let's go ahead and compute that. That would be the integral of t plus 1 multiplied by e to the negative t dt, and that is the opposite of t plus 2, e to the negative t. Let's do the same for v2 of t. We would have the integral of t, e to the t divided by the opposite of t, e to the t dt. Of course, we're just integrating, whoops, negative 1, and we come up with the opposite of t. So now that we have our v1 of t and v2 of t, our two functions, we can come up with our particular solution, which is going to be y1 v1 plus y2 v2, which is equal to the opposite of e to the t, t plus 2 e to the negative t, minus t plus 1t. And simplifying that, we come up with the opposite of t squared minus 2t minus 2. And that is our particular solution. As you can see, we have y2 of t right here. So we will, by superposition, omit this and just go ahead and come up with our general solution that already included y2 of t, a combination of it, c1 e to the t plus c2 t plus 1 minus t squared. There is our particular solution. We'll go ahead and write. Okay, let's look at our next example here. We will again be given, or we are given, two linearly independent solutions, and we will now write the general form of our differential equation. So we have y double prime plus 1 minus 2t all over t y prime plus t minus 1 over t y is equal to e to the t. So we see here that e to the t is equal to g of t. We have two linearly independent solutions given here, and we can now compute their Wronskian. So we have the Wronskian of y1 and y2 of t, and that's equal to e to the t multiplied by e to the t natural log of t prime minus e to the t prime multiplied by e to the t ln of t. And when that is simplified, I will go ahead and work that out. So we have e to the t multiplied by and that's just equal to, oops, I'll just go ahead and leave that, 1 over t e to the 2t. So we could write that as t to the negative 1 e to the 2t. So that is going in the denominator of our solutions, v1 and v2. So we can, you can remind yourself of those formulas, but we have v1 of t is equal to the opposite of the integral. We have e to the t, ln of t, divided by, and here is our Wronskian, t to the negative 1, e to the 2t. And there we have our g of t here, and then we also have y2 of t, dt. And of course we have v2 of t, and we can go ahead and simplify that. That would be equal to the opposite of t, ln of t, dt, and you can use table or a form of integration to come up with negative 1/2 t squared ln of t plus 1/4 t squared. Okay, so v2 of t is equal to the integral of e to the t multiplied by e to the t, and that is our g of t multiplied by y1, divided by our Wronskian of y1 and y2. And that comes out to the integral. You can see that worked out beautifully, of t dt, and that's equal to 1/2 t squared. So now we can write our particular solution as negative 1/2 t squared ln of t plus 1/4 t squared, all multiplied by e to the t. That's our v1 multiplied by y1 plus, and here we go with our v2, 1/2 t squared multiplied by y2. And if you simplify this, you will see that it comes out to 1/4 t squared e to the t. So you can see that this term, I'll go ahead and write it out. So negative 1/2 t squared e to the t ln of t plus 1/4 t squared e to the t. And then here is our positive term. That cancels with that term, and we come up with our particular solution as 1/4 t squared e to the t. So now we are able to write our general solution as y of t is equal to 1/4 t squared e to the t. And here are our two given solutions. And this was our solution to the homogeneous equation. And that concludes this lesson.